Green's theorem. Green's theorem has two forms. The first one is the closed surface integral for a surface that surrounds volume V. The integral d sigma dot u gradient V minus V gradient U, where u and v are scalar fields, is equal to the volume integral d tau u Laplacian del square V minus V Laplacian u del square U. Second form is for the closed surface integral d sigma dot u gradient of v is equal to the volume integral d tau gradient of u dot product with gradient of v plus u Laplacian v del square v. Okay, so in order to prove Green's theorem of both forms, we're going to consider two scalar fields u and v and consider the divergence of u gradient v. Now, using subscript summation notation, the del operator, remember, is in Cartesian coordinates del xi ei hat, and this is a dot product with the scalar field u. Now the gradient of v is del xj applied to v in ej hat direction. Okay, so we have ei hat dot product with ej hat, so we can consider that. So we have del xi, and we have the dot product with ei hat and ej hat, the two unit vectors, and then we have the scalar field u del xj applied to v. All right, and now we can recognize that the dot product of two orthonormal unit vectors, ei dot ej hat, is Kronecker delta ij. So this is equal to del xi applied to u del v del xj, and then I have Kronecker delta ij. I and j must be equal, otherwise it's 0. And this is equal to, now I'm going to substitute j for I, del xj, derivative applied to u del v del xj, the partial derivative with respect to xj. Okay, now we're applying the derivative operator del xj, so that means we have to first take the derivative of u multiplied by the second term. So we have del u del xj multiplied with del v del xj, and the second term we're going to leave u alone and apply del xj on del v del xj, which means we're taking the second derivative of v with respect to xj. Okay, and this is basically equal to, I can now recognize the first term here is del u del xj and del v del xj. This is a dot product between two gradient operators. So gradient of u dot product with gradient of the scalar field v. That's the first term, plus u, the second derivative basically implies the Laplacian del square v. All right, So we reach the conclusion that divergence of u gradient of v is divergence of u gradient of u dot product with gradient of v scalar field plus u Laplacian del square v. Okay, so let's call this our star equation. And if we switch the places of u and v, now this is divergence of v gradient of u. Reading the result here, again we will have this time gradient of v dot product with gradient of u. All right, and then we have plus v Laplacian operator applied to u, del square u. So we have obtained these two equations. Now what I'm going to do is subtract the 2-star equation from star equation. So divergence of u gradient v minus divergence of v gradient u. So that's what I'm going to do now. Divergence of u gradient of v that's the star equation minus the divergence of v gradient u that's the double star equation. This is going to be equal to, now you can see that the first terms are the same, so it will be u del square v minus v del square u, because these will cancel out. So I will have u Laplacian applied to v scalar field minus v Laplacian applied to u scalar field. Okay. Now, what was I supposed to look at? U gradient v minus v gradient u. So if I write divergence of u gradient v minus the divergence of v gradient u, which means I'm taking the divergence of u gradient v minus v gradient u, the volume integral of divergence u gradient v minus v gradient of u d tau. If I take this volume integral, what is this equal to? Now Gauss theorem tells me if you take the volume integral of divergence of a vector, which is this vector here, you will get the closed surface integral d sigma dot v. So v vector is this vector. So this will give me the closed surface integral for the surface that is at the boundary of this volume. We're going to get d sigma dot u gradient of v minus v gradient of u. And what have I used here? I have used Gauss theorem. So I have recognized the vector v to be u gradient v minus v gradient u and substituted into Gauss theorem. All right. So indeed, so we find that our closed surface integral d sigma dot product with u gradient v minus v gradient u is the volume integral d tau u del square v minus v del square u, because u gradient v minus v gradient u, d sigma dot this is divergence of this, but divergence of this is equal to, as we have shown, u del square v minus v del square u. So we have proven Green's theorem. Now if I use the star equation instead, or if we use the star equation, we have the volume integral d tau divergence of u gradient of v, the star equation, divergence of u gradient of v, and that's equal to, using Gauss theorem, closed surface integral d sigma dot product with u gradient of v. Once again, I have applied Gauss theorem, recognizing my vector v here is u gradient of v. That's Gauss theorem. All right. And for u gradient of divergence of u gradient of v, I can substitute this result from the star equation. So I can say that this is the closed surface integral d sigma dot product u gradient of v is equal to the volume integral d tau, because divergence of u gradient of v is gradient of u dot product with gradient of v plus u Laplacian del square v. This is the second form of Green's theorem. Okay, so Green's theorem suggests the closed surface integral d sigma dot u gradient v minus v gradient of u is equal to the volume integral d tau u del square mi minus v del square u. So where closed surface S is surrounding the volume V. The second form, closed surface integral d sigma dot u gradient v is the volume integral d tau gradient of u dot product gradient of v plus u del square v. In order to show this result, we've considered the divergence of u gradient of v. Using subscript summation notation, we have found that this is gradient of u dot product with gradient of v plus u del square v, Laplacian square. So this basically helps us prove the second form, where we have the d sigma dot u gradient of v. D sigma dot u gradient of v closed surface integral is equal to the volume integral d tau divergence of u gradient of v, using Gauss's theorem, recognizing this vector v as u gradient of v. But since we have shown that divergence of u gradient of v is equal to this, this proves the second form of Green's theorem. If I consider the divergence of v gradient u, That's the dot product of the gradients of v and u plus v Laplacian u, and subtract this equation from this equation, then I obtain divergence of u gradient v minus divergence of v gradient u, which is the divergence of u gradient v minus v gradient u, it's the same thing, is equal to u del square v minus v del square u. So divergence of this volume integral is equal to closed surface integral d sigma dot this vector u gradient v minus v gradient u, according to Gauss' theorem. So this integral is equal to integral v d tau, divergence of this, which we have shown to be u del square v minus v del square u. So we obtain the first form of Green's theorem.